Kepler's second law states that a line joining any planet to the Sun, sweeps out equal areas in equal intervals of time. That is, their aerial velocity remains constant. Now, after discovering the first law, Kepler wanted to know how the planets moved in their elliptical orbits. He found that planets were moving faster when they were nearer to the Sun and were moving slower when they were farther from the Sun. He was awestruck by his observation and wanted to find at least a mathematical reason for this strange phenomenon. First proof of Kepler's second law. This is the easiest proof available for Kepler's second law. See this picture. Let us bring the conservation of angular momentum in the picture. Angular momentum conservation law states that unless an external force is applied on a system, the angular momentum of that system remains constant. Angular momentum is represented by J vector. J vector is equal to m into v vector cross r vector. V vector represents the velocity vector and r vector represents the position vector of the planet, keeping the Sun at the origin. Let us consider the motion of the planet from A to B in time t. So J1, initial angular momentum J1 will be mv1 cross r1, which is m into delta r1 by t into r1, breaking the velocity equal to delta r1 by t. So it is becoming m delta r1 by t into r1. When the planet moves from C to D in the same time interval t, then J2 will become mv2 cross r2, and similarly we break that to m delta r2 vector by t cross r2 vector. And by conservation of angular momentum, J1 is equal to J2, as both J1 and J2 are changing in time interval t. So m delta r1 by t into r1 is equal to m delta r2 by t into r2. We are just substituting the values. Cancels and t also cancels, so it is becoming v1 vector cross r1 vector is equal to v2 vector cross r2 vector. That is, v1 r1 is equal to v2 r2, which is a constant k. So we are just proving that v is inversely proportional to r. From the equation we can conclude that to keep the value of velocity into distance from the Sun a constant, whenever r decreases, v increases, and vice versa. This means that when any planet comes closer to the Sun, its velocity increases, and when it goes away from the Sun, its velocity decreases. Now let us understand what exactly Kepler's second law is stating. It is stating that when the planet is moving from A to B, it is sweeping an area which is shaded on the left side of the figure. The planet is doing this in time interval t, and in a same time interval t, if the planet moves from the position C to position D, it will again sweep an area which is shaded in the right side of the diagram. Now, as both the sides have been swept in equal time intervals t, both the areas will be same. That is, the aerial velocity of the planet will be constant. This is Kepler's second law. Second proof of Kepler's second law. See this diagram. Let us consider the geometrical argument as shown. As the planet moves from P to P dash, in a small time interval delta t, the radius vector r sweeps out an area delta A. Therefore, delta A is equal to half into r vector cross delta r vector, from formula of area of triangle, half into base into height. So dividing both sides by delta t, we are getting delta A by delta t is equal to half r vector into delta r by delta t. Proceeding to limit delta t tends to 0, dA by dt is equal to half r vector cross dr by dt is equal to half r cross v. Dr by dt is velocity vector. So it is becoming 1 by 2 m r into mv. We are multiplying and dividing the RHS by mass m. So it is becoming half 1 by 2 m into r vector cross mv. But r into mvr is angular momentum j, and the angular momentum of the planet with respect to the sun is constant. So dA by dt is becoming 1 by 2 mj. M is constant, the mass of the planet will always remain constant, and we have just proven in the previous equation that j, the angular momentum of the planet, always remains constant. So m and j are both constant. That means dA by dt, that is the aerial velocity, will again remain constant. As j is constant under a central gravitational force, the aerial velocity dA by dt is constant. This is Kepler's second law, whose conclusion is the planets move faster when they approach the sun, when they comes nearer to the sun, and they move slower when they move farther away from the sun. Now, Kepler's second law is not only applicable in case of planets moving around the sun, it is applicable in case of moons moving around the planets, satellites moving around the earth, and also planets moving around other stars. But remember, it is not, Kepler's second law is not applicable in case of stars orbiting around the supermassive black holes of all galaxies, because at that scale another thing comes into the picture, which is the dark matter.